Hi, it's Ryan. Today we're going to talk about a couple examples, first starting with series circuits. So this will be an example for a series circuit. We'll also do a parallel and a combination. In a circuit problem, oftentimes you'll be asked to solve for the circuit. What this will really be asking then is to determine the voltage across each component. The current through and the power dissipated by each resistor. We're also going to determine the equivalent resistance and the total power dissipated by the circuit. So that's what we're going to do, and in a problem written like this, you would have probably been given a picture with some more information on it, since nothing is really given in the problem statement. And so I'm going to show the series circuit where we've got our power supply and our three resistors in series together. Keeping in mind, a series connection is when there's only one loop for the current to pass through. In other words, there's no junctions or anywhere for the current to split into new currents. So there is our circuit with its components. And as always, I'm going to show that if this is a closed circuit with a power supply, it will establish a current throughout the entire circuit, and that current has nowhere to change, nowhere to break up. There's no junction, and so the current will just remain the same. We'll also have been given a few of these numbers. So V is 12 volts, R1 is 61 ohms, R2 is 200 ohms, and R3 is 142 ohms. And so this is the sort of problem that you might see. This is a fairly simple problem with just three resistors in series, as we'll see. So in order to solve this, I think that a really good habit to have is to develop an answer table. Even before we get to any real work, we can put down a table that comprises all of the possible solutions we'll be getting. So we have a column for resistances, I for current, V, which is of course IR, for voltage, and P for power, which is always IV. And then we can go ahead and put in our resistors, because those are constant. And we can't just go ahead and say anything else yet. We need to solve for this stuff. And so the first step to solving for this would be to simplify the circuit. In other words, let's determine the equivalent resistance for the circuit. The equivalent resistance for the circuit, and of course for any series circuit, R equivalent for any series is always the sum of the resistors, and so it's pretty simple in this case. It's R1 plus R2 plus R3. So I can go ahead and substitute in those values with their units. 61 ohms plus 200 ohms plus 142 ohms would yield the equivalent resistance for the circuit, which is going to be 403 ohms. And notice there's not really a spot for that in my answer table, but I'm just going to box it in. Now what we've effectively done is simplified the circuit. So we've created a simple circuit now where we have one equivalent resistance and one power supply. And of course the same current that the battery is establishing through the circuit. With a simple circuit, it's simple to apply Ohm's law. So we could say using Ohm's law, we know V for this circuit, so V total is equal to I total times R equivalent for the circuit. V equals IR. If we solve then, we have V over R equivalent is I total. So the total current established into the circuit by the battery would be 12 divided by 403. And that will end up giving us amps. It'll be 0.0298 amp. And so really this means the total current, another way to write it would be 29.8 milliamps. That's often how you'd see it in the real world, but either answer is acceptable. Well, knowing that that current has nowhere to change, as soon as we determine the total current, we've actually determined 3 solutions in our answer table. So without really thinking much more about it, I can simply go ahead and say that, well, this is 29.8 milliamps, this is 29.8 milliamps, and this is 29.8 milliamps because I is unchanged. And if we know R and I, we can go ahead and solve for V. If we multiply I times R for each of these, not forgetting to use the amp measurement and not the milliamp measurement. So if you take the 0.0298 times 61, you'll get 1.82, 5.96, and 4.23. And I'll bet you that a way we could check this solution would be to add these 3 voltages, and I'm assuming they should add up to the total voltage supplied by the power supply. In other words, 12 volts. Now we did round, I rounded those 3, so we might be slightly off by like 0.01 or something, but that's due to rounding. I rounded the current 0.0298, and that rounding got propagated in each multiplication. So that's a perfectly acceptable answer. Knowing I and V, we can also calculate the power dissipated by each component. If we do that calculation, we would have 0.054 watt, 0.128 watt. Actually, that's a 7, I believe, not a 2. And we have 0.126 watt. And so one way to get the total power dissipation is to simply add those together to get 0.358 watt. Or we could use this simple circuit picture that we created and use P total equals I total V total, and that will end up yielding the same thing. If we put in the 0.0298 amp times the 12 volts. We'll end up getting the same answer again. So as you can see, there are multiple ways to get these solutions as long as you keep track of your series circuit rules that we got in class. And that's an example for solving a series connection in a circuit. You can use this for this methodology for really any circuit, but we've only covered so far in this example the ideas or the laws or the rules for series connections.